I think the question, how is the bridge between teleoperated and autonomous robots, brings us well to the next speaker, who is Sethu Vijayakumar from the University of Edinburgh. Sethu, welcome, great to have you here. He is one of the persons who applied machine learning in robotics at times which were not a hype in robotics yet. So he is somebody who bridges the gap between machine and human intelligence since many years. And today he will talk about shared autonomy and the future of interactive robotics. So welcome, Sethu. Please, the stage is yours.
Thank you, Alan, for the exciting opportunity. It's a pleasure to join you guys from the unusually sunny Edinburgh. As Jessica said, it would have been great to meet up with all of you in Munich, but this is the next best thing that we can do. So if I can have the first slide, please. Yeah. So the topic today nicely dovetails from the previous speaker in terms of trying to look at the two extremes of full autonomy versus teleoperation. And in my opinion, really the challenge is, how do we marry the best of both worlds? How do we take contextual information from humans, exploit it in tasks that are still hard for robots, but still exploit the strength, the accuracy, and the repeatability of robotic systems? And that's where this work comes in. So if you go to the next slide, so there are two extremes. On the one hand, we are very good at getting robots to repeat things using various kinds of inputs, so joysticks to sort of human-based sensors. At the other extreme, if you just click through, if you can just click. Yeah, thanks. And the other extreme is fully autonomous systems, where the robots are making decisions on its own, taking environments, sensing into account, and really not having humans in the loop anymore. But if you click again, the real challenge is something called shared autonomy, where again, if one more click would get you to this topic of why we have this combination of fully autonomous behaviors or teleoperations is not very suitable for some of the applications I list here. So everything from prosthetics, self-driving cars, to humanoids and nuclear decommissioning kind of settings, there are some challenges. So if you go to the next topics, and the real challenge arises because there are some interesting open areas that have not been fully solved. And this comes from the fact that the robots of today have to interact closely with multiple objects. We've got noisy sensing, there's hard to model real world dynamics, there are time delays, and more importantly, when humans interact, then we have got unmodeled user intentions and constrained environments. So because of these, really what you want is a system which is able to dial between full autonomous behaviors and teleoperation, and somewhere in between, not just uniquely within a task, but change that within a task. And that brings additional problems, additional issues, additional open challenges that needs to be solved. So if you go to the next slide. So in our group and in the robotics community, we've been using, as Aline mentioned, machine learning techniques to drive some of these challenges that are coming out of this concept of blending the human in the loop behaviors and the autonomous aspects. So definitely perception, so localization and scene understanding, but more importantly, adaptive whole body motion planning. So how do we ensure that in very dynamic situations, the whole body motion planning takes into account the multiple sort of embedded and hierarchical task plans, whether be it maintaining balance, avoiding contact, exploiting contact. And that's where machine learning can play a big role in terms of dealing with unexpected environments. And finally, if you just click through and show the video, what you'll see here is that in a real scenario, what you really want is the robot on the live site making fair number of decisions on its own, like reactive behaviors, collision avoidance, but the human is getting kind of feedback based on things that they have planned, where the human can give some high-level goals in terms of pick this, put it here, and most of the decisions in terms of obstacle avoidance, navigation, decision on which arm to use to pick up things, what is most robust behavior is done autonomously by the robot. So, and that's where the thing that we want to drive towards in terms of blending the best of both worlds. Now, if you go to the next slide, so if you look at what are the interesting areas where these are really important. So if you take the example of navigation on a very difficult platform like an oil and gas platform. So if you play the next video, you'll see an example of a quadruped robot, and this is a video courtesy of Marco Hutter, navigating very uneven terrain with slippery footsteps, having to navigate obstacles. So this is clearly a domain where we want robots to do as much autonomous behavior as it can do, but still have humans validating things in between. So we've seen robots, quadrupeds walking around. So is the challenge of quadruped locomotion solved? And the answer is no, because if you click through the next bit, you can see an animation on the top, and maybe one more click gives you a video at the bottom, is challenges where quadruped locomotion with interaction with the environment, when it is manipulating objects, touching things, pushing buttons, turning walls, robustness is quite, it's a fragile situation. And we want to create novel machine learning techniques that builds on physics, that builds on exploiting known knowledge and bias to actually plan motions that are inherently robust. And that's where some of our research in this area goes on. And if you click to the next slide, another very interesting domain is in the domain of scenarios where the object or the robot being manipulated is really far away, for example, in space. So if you click through the next video, you'll see an example of our NASA project with the humanoid Valkyrie navigating a very complex, uneven terrain. Here, a lot of the decisions in terms of sensing, navigation, where to place your foot is done autonomously, but the human still has a sort of punctuated autonomy in terms of validation of various steps. So this is a perfect domain where teleoperating due to delays, due to uncertainty in sensing becomes really hard. And that's where we're pushing this domain. So not just in this area. If you go to the next slide, even relating to the previous talk, one big area where shared autonomy is a big challenge is in the medical domain. So whether be it exoskeletons, whether be it surgery, we are interested in exploiting human knowledge, human contextual decision making, while ensuring that some of the mistakes that human activity brings in is avoided. So if you play the next video, the domain where we've been trying this out is in the domain of lower limb exoskeletons, where you've got human strapped to an exoskeleton. In this case, a healthy patient who's being rehabilitated from a sports injury. And in this case, some of the assistance, it's not obvious what is the right level of assistance to apply, because the more assistance you give to the person doesn't really recover some of the muscle activities. So you have to have a scenario which is adaptive, which reacts to what a human is achieving and successively changes its assistance on an as-need basis. And this is where some of the open challenges comes in. So if you go to the next slide, I just want to spend a minute looking at what are, in my opinion, still interesting underlying open scientific challenges. So safe actuation in dynamic human-robot interactions is very, very challenging. People have done a lot in software, so real-time adaptation, model predictive control, making that fast enough. But if you click through here, just one, one of the big challenges is how can we build in some of this safety in hardware. So we've done a lot of work along with some exciting work at DLR on compliant actuation. So the next challenge, if you just click through once more, is reducing the sim to real gap. In other words, how do we ensure that the experiments that we're doing on real robots are actually replayable in simulation and can be reproduced on real robots? And finally, verifiable and explainable methods, if you click through once more, is understanding the limitations and vulnerabilities of the deployed systems is another big challenge. So the last slide I have is if we go to the next one, some things we haven't discussed are things like what are the key open questions in shared autonomy. So not just in robotics, but when we talk about shared autonomy, what are the interesting open challenges? So things like responsibility and explainability becomes a lot more blurred when we are blending between human input and autonomous behaviors. When and how fast do we transfer control back and forth? And in learning systems, when your system identification is constantly evolving and changing, that brings another additional challenges. And these are the kind of things that we're tackling. If you click on the next button, at the Alan Turing Institute, at the University of Edinburgh, and in our group. So thank you very much for the opportunity. I welcome any questions. And again, if you go through the next slide, some of the work that we're doing is, if you follow the link here, you can get access to some of the exciting work that we're doing in this domain. Thank you.
So thank you very much, Sethu, for this great talk. And we have seen actually a lot of research is happening at the border between teleoperated and autonomous robots. It was the topic of Antonio's talk. It is the topic of your talk. So it's the place where a lot of things are going on. And you addressed actually very, very clearly what the challenges are. Explainability, understandability, especially if you have this interaction. Could you say a few words more about how do you handle, for example, the handover between the human control and the robotic control? Because the human changes the world, right, while he's operating. Are your robots aware of what the human did, about what changed the world, and what are the new situations for their autonomous operation? How do you handle that?
So that is a very interesting and challenging topic, an active area of interest and research, and it has to be tackled in a very domain-specific way. So, for example, in the domain of rehabilitation and shared control, when we have wearable robots, so here the human input is through the actual muscles being actuated, the residual muscles actuating, and that's the scenario where we have to do the best job of sensing what these residual muscles are doing. And then we have various ways of tackling. So, for example, if you've got a combination of FES and, say, an exoskeleton actuating and the residual muscles, so we have this concept of control authorities, where as long as it is these control tubes or control authorities, it is respected, you do not do the intervention, and as soon as it leaves that control authority, the next level, whether it's FES or exoskeleton, that kicks in. And so this is a kind of an architecture where we can blend between these control architectures and ensure a hierarchy is maintained. In some cases, like human-robot collaboration in co-manipulating something, there it's even trickier, because there's a notion of the policies that you're building. If you think about classical reinforcement learning or inverse reinforcement learning, the policies that you're building are very much dependent on human policy estimation and adjusting the policies based on that. So there's some work that we're doing on combining inverse reinforcement learning with human intention detection to adapt the policies that a robot would incorporate. So it has to be very, very domain specific.
Yeah, thank you. Maybe another very short question at the end. We learned from the cobots applications that already their certification was challenging, although the environment was more controlled in industrial area. Now we are talking about new exciting areas with robots which are more intelligent, and you have this blending between autonomy and AI. How do you think certification will be handled for all those AI and complex environments? And again, I ask every speaker, what's your timeline for seeing those things on Automatica?
Again, very good question. So at the Alan Turing Institute and in UKRI, so it's in the UK robotics land space, we've just kicked off a big program called Trustworthy Autonomous Systems, or Trustworthy AI. And really, I think there are two aspects to it. One aspect is governance. So how do we define, build rules about what is safety, what is reliability, because the traditional norms of safety and the kind of ISI standards and all those things, they are really not fit for purpose in this blended scenario. So the real question is, to begin with, how do we limit the range of control of a robotic system, of a human, and how do you segregate them and how do you bring them together? Obviously, the next challenge is how do we look at it at a system level? How do we look at it from not just individual components, but at the level of systems? How can we re-specify the goals, re-specify validation methods and schemes? And we have done this with aircraft systems and space systems. So it's a matter of taking those principles and working them down into some of the areas that robotics have been looking at, going away from segregated systems to blended systems.
Thank you. Thanks a lot again for this great talk. Thanks back to Edinburgh, Professor Sethu Vijayakumar.